Okay, today we're going to look at two of the really important variants of texture mapping. In this lecture, reflection and environment maps, and then in the next lecture we'll talk about bump mapping. Now, these are techniques that we use all the time. I'll show you some applications at the end of this lecture that we use over at the Arts Lab with producing things for domes. But let's start with going over the kind of effects we're going to try and create first with cube maps and spherical maps, which are two ways of doing reflection or environment maps, and then, as we said, next lecture we'll look at bump maps. So the things we're trying to do is move from this smooth shading and basic texture mapping, where we would put a pattern on these polygons that we make up this little ball, to having a more reflective type of surface by using the environment in which we want to place this object to form the texture map that we then place on it. So one of the things we'll see is that environment mapping is really an application of the sort of the straightforward texture mapping we talked about in the last couple of lectures, with this added part that how do you get this environment and construct the necessary texture maps. In the next lecture, when we talk about bump mapping, that's going to have a fundamental difference in that we really are changing the rendering process. Here we do the standard rendering process that we did over here on the left, and change only when we get to the fragment shader by using the texture map to alter the color. Here we're doing a much more complex procedure that involves playing around with the normals at every fragment that we're going to render. So we'll separate the two out. In this lecture we'll do this one, this lecture, and the next lecture we'll do bump mapping. Okay, so let's talk about environmental or bump mapping. So the idea is to create the appearance of a highly reflective kind of mirrored surface without doing global calculations. We know that we can do this with a ray tracer by just tracing the rays, and the rays will pick up the reflection from objects and do that. But we know that that's not a real-time process, and so how can we get something that looks pretty good without having to do this global calculation and still use the hardware that's in the pipeline of the GPU. So this technique was created quite a while ago by Jim Blinn, who created many of the techniques that you're going to see, but it became famous to the public when it was used in movies like The Abyss, if you remember that, and Terminator 2, where you had these sort of metallic kinds of Terminator 2. I remember had these metallic kind of mercury liquid-like objects, and they were reflecting the environment all around them. Now, because we can do it so well with GPUs, it's pretty standard to use that in video games to create these kind of reflective effects. And as we said, it's going to be a form of texture mapping. So let's look at the sort of the basic ideas, and start off with this: that if I'm a viewer and I'm looking at little surface, and we can always say that locally it looks like a little polygon if I just concentrate on a small area. And if this is a reflective surface, then if I'm the viewer over here, then I'm going to see what happens by doing the angle of incidence, angle of reflection, and compute the reflected direction, and I'm going to see something off in this direction. Now, it also the color that I get might also be modified by the properties of the surface. It's going to absorb some of the light from here, and it may have other effects like some emission and scattering, but the reflective part is due to that I'm seeing something off here in the distance at the angle of a perfect reflection. And obviously that changes as the local shape of that surface changes, because that's going to change the normal. Now let me inject a slightly different view of this, which is going to be equivalent, which says, what if I put a hemisphere, or a sphere, let's say a sphere first. I put a sphere around this whole area. So now, what if I look at this as a two-step process? Remember, we looked at this idea of intermediate surfaces in a couple of lectures ago when we first presented texture, let's use that idea again. It gets used in many, many places, and people study atmospheric physics. This is a very standard way. Astronomy, it's a very standard way to look at things. We put a big ball around it, and I project this object out here, the object I'm going to see as a reflection, I'm going to project it onto the surface of that sphere. Now, before, when we did that, we said, well, the reason we want to do that is it's going to make the texture mapping simpler to be mapped from a surface that has a very simple geometry like the sphere and later a cube. And that's going to be true here too. Now, the thing to keep in mind here is that if I'm the viewer, I cannot tell the difference of whether I'm looking at this, let's say a cloud, way out here, or I'm looking at it mapped to an intermediate surface. You have to think about that for a while, but that is really the basic of an awful lot of science and ways of analyzing effects, is to map everything to a sphere and then say if I have it on the sphere, then I could do everything, and the viewer cannot tell the difference. I mean, let me give you a very simple example of that. If you go to a planetarium, and I think most of you have gone to a planetarium, and you see the stars out there, it looks kind of real in the planetarium. Well, it's not real. They're not out there an infinite distance away from you. They've been mapped onto the spherical surface of the sphere, but from the viewer's perspective, it's exactly the same. And then we're going to take advantage of that by using an intermediate surface, which a sphere is really easy to see physically what's going on, but it doesn't lead to very simple computations. So it's used a lot. I'll have one reference to that at the end. But the one we're going to focus on is cube maps. So rather than put a sphere around the whole thing, I'm going to stick the point I'm looking at inside of a cube. You could also use cylinders, but we're going to stick with cubes because that's what's supported by WebGL. So here's the equivalent view of the original process plus equivalent to using a sphere. And I'm going to project that cloud out here onto the surface of this cube. Now, it could also wrap around. Part of it, if I move this over a little bit, part of it would appear on the top surface, part of it would appear on this right side. As long as I do the mathematics carefully, the viewer cannot tell whether that's still not a cloud way out here in the distance, or that this is a cube versus a sphere. It looks correct if I do the projection correctly. So why is that an advantage? Well, to use the cube over a sphere or something else? Well, it's because these surfaces, I can align them with my coordinate axes, and this then becomes a surface of constant z, and the back plane is a surface of a plane of constant z, and likewise for the right, left, top, and bottom. Now, if I do that, I can now index into what's called a cube map. So if I look at this as a two-step process, where first step is to project onto the cube, I form 6 images. Potentially the bottom is in here too. So I have 6 images formed by the projection onto the cube, the top, bottom, right, left, front, and back images. And now when I want to do a rendering for what's somebody sees inside, for these objects inside and a viewer out here, I now can do the reflection again and see where that reflected vector hits not the original object, but hits the cube. Okay, so let's look at that. So here's the standard computation for the reflection direction given the normal at the surface, which I probably should have drawn in. And we're assuming here that the object is at the origin. Now, we can always make changes for objects that are not at the origin, but if you want to make the equations to understand this a little simpler, think about the object as being at the origin, and here's the equation of the direction of a perfect reflection. Now, how do I know which surface of the cube it hits? It turns out that's really simple. All I have to do is look at the XYZ directions, dx, dy, dz, the directions of this cube, and the one that has the largest magnitude, we have to take out the sign in this calculation, the one that has the largest magnitude is the surface that I'm going to hit first. So if this goes off in the direction 1, 2, 3, it's going to hit the top surface z equals 1 before it hits any of the other sides of the cube. Likewise, if it was 1, 2, minus 3, it's going to hit the minus if this is the unicube, it's going to hit the -1, z equals -1 surface first. So that allows me to compute where it's intersected very quickly, because just the largest magnitude tells me which of the 6 surfaces I'm dealing with, and then I could then essentially project that the point that the direction I'm given into 2 coordinates on the surface, z equals 1, z equals -1, or the x and y's equal to plus and -1, and that's going to give me texture coordinates. So it's a very straightforward process. It's implemented in OpenGL and WebGL for cube maps. So let's sort of just summarize that. WebGL, you only have cube maps. OpenGL supports, desktop OpenGL supports sphere maps too. In the book, in the notes, you'll see the derivation of the equations for a standard way of doing the sphere map, but we're going to focus on cube maps just because we're using WebGL. And also they're very, very simple to do. So your job is really a 2-step job, and this is our first example of multi-rendering, where to see one scene we may have to do multiple renderings. So one way is that we actually use a bunch of cameras and take a map of the picture of the environment. So you could do the following. You could come back here. You could actually put the camera right here in the middle, and I'll show you a picture where we're doing that with animation software, and take 6 pictures. Point the camera straight up and you'll get this top surface image, and you can use that as one of the 6 textures, and likewise point it to the right, left, front, back, so on. And so you can get 6 images as JPEG or some other type of image. You can also form the images if it's a totally virtual scene. You can form that image by just doing a rendering. So I could say, well, look, what is the image looking straight up if this is a totally virtual scene? Well, that's just a question of where is my viewer. Now I'm putting the viewer at the origin instead of the eventual place I want to look at this from. But in order to get this top view of the virtual scene, I put a camera over here and take a picture looking straight up. And what do I get? This is the image that I form right here. And now I'm going to use that image as a texture for part of the cube map. And I do it 6 times to get the 6 images that form the surface of the cube. Okay, so we can do that. And now we do the texture map to the object, where the cube map will do this correctly. So let's look at what it looks like in detail with WebGL. Okay, so as we said, we form the cube map by defining these 6 textures. They're put inside of a texture object. So rather than having a single texture within the texture object, there's going to be 6 of them, each which has a different identifier telling you which surface it's from. In the sampler, it's incredibly simple because all you're doing is using a texture cube sampler instead of the 2D sampler. So the function is called texture cube. You give it the texture object that you formed. We'll see some code in a few minutes. You give it the pointer to the object, and then you give it the texture coordinate. Now, the texture coordinates are 3D. They're the direction. They're the direction that you're pointing in, and it will figure out which component has the largest magnitude and select the correct. Figure out what the texture coordinates are on that surface. And actually, that is often very much simpler than what we did with normal texture mapping, because generally those coordinates are just the location of the vertex or something very close to that. So it's easy to get those texture coordinates to pass in. So really, it's a one-line change once you've set up the correct texture object. Okay. So what about the shaders? Well, it's pretty. One thing you have to be careful in doing this is that these maps are usually computed in world coordinates, just because that's an easy way to do with a virtual or real camera. You sometimes have to be careful if you're doing some modeling. If you're doing instancing and you're bringing in instances into the world environment, you have a matrix that converts you from the definition of the objects in their own systems in the modeling frame and converts that into their positions in world coordinates. So often you have to be a little bit careful of that and maybe pass a modeling matrix onto the shaders. But I think there's some examples of that you can find fairly easily. One of the other places this gets used a lot, and I'll maybe send out some web pointers to this. I can't put them in the recordings, is to use some method to generate incredibly neat effects in real time for those 6 surfaces. So there's a wonderful one I saw a week ago where they're doing waves in water, and the waves in the water on each of the 6 surfaces are computed actually with a little ray tracer the person built. But the way that he gets it to be in a 3D world is through a cube map onto his objects, and it's a very, very startling effect that's done using a combination of WebGL and other rendering techniques to form the 6 cube maps. Okay. There's some issues with this. You have to be a little careful. This isn't really a ray tracer, so you have to understand that reflection maps are not exact. And there's a couple of things that make it different. One is you're assuming that the environment you're mapping is very far away when you do that intermediate surface. You have to worry about things, or you can't have things that are self-reflective. So that says you can't have what are concave objects that reflect upon themselves. You can't capture that with an environment or reflection map, although you could do it with a ray tracer. But probably the biggest lack is that you don't get multiple reflections. Effectively, what you're doing to get a reflection map or a cube map is to take the object out of the scene, put this camera where the object was, and take the 6 images. So now you've eliminated the possibility of the environment bouncing off of that object and then reflecting some light onto the other objects, which get reflected back. So you can think of it this way. Suppose you were doing a reflection map in an environment that had a mirror in it, where in real life, standing there, you could see yourself in the mirror. You won't capture that with a reflection map because you've removed yourself from the image. Computationally, to do it correctly, you need a reflection map for each object in the scene. Remove it, put the camera there, compute it, and then get a different one. Now, that's generally not done because it's so computationally intensive. However, generally the way people get around this, and they also do a similar thing to getting realistic images with ray tracers, is they don't do reflections off anything but a couple objects. If you look at a real scene, there aren't that many objects that really need to have true reflections on them. Unless you compose a scene with a bunch of metallic balls in it, generally there'll be only a couple of objects that need reflection maps, or you only want to focus on one object, so you only do its reflection map. And also, if the viewer moves, we did this calculation, given all the viewers here, let's compute where the direction of reflection is and get the texture maps. Well, if I move the viewer, then that reflection direction changes, and now I have to, in principle, compute the cube maps all over again. However, it sounds like, oh, these are all really bad factors, but in reality, people can get some wonderful images with cube mapping, much better than you might expect from looking at the slide. So let me finish up showing you a couple of examples that we did with some work we're doing over at the Arts Lab. Actually, we've been doing this for a bunch of years. Here's some images that Hugh Walker, who is our animator, artist there, created for me. She was working with Maya and created some artificial images so I could show you this. So here, what you see is maybe a little difficult here. She put 6 objects in the scene: the sphere, the cone. There's a little donut up here. This is a tetrahedron, cylinder, and a cube, and also put some labels so you can see which one. So then she put 6 virtual cameras at the origin. If you blow this up a little bit, you can sort of see it's a sort of a wireframe picture of a movie camera, and took the 6 images. So here's 2 of those images, the front and the top image. And then what we did is those formed our cube. So if you want to look at the cube, here's our cube. with those. Now, we're doing this, I'm looking at this cube from the outside. In our application, we're looking from the inside, so everything gets inverted. If you were sitting inside at the origin, then you'd see left and top and front coming out as you would expect. If you unfold the box, it looks like this. Now, in our application, because we're only generating up for projecting onto a hemisphere, we don't need the bottom. But if you looked at the sixth image, we could tack it on over here as the bottom image. But we usually you'll display it as an unfolded cube. Now let's look at what that looks like if we're using these images in WebGL. We use the texture map 2D, but now instead of saying that what we're doing is GL texture 2D, we're doing texture cube map, and there's 6 possibilities: the positive X map, the positive Y map, Z map, and then the negative X, Y, and Z maps, and we give each of them an image, which would be one of these images like we formed over here. So we have 6 statements like this, all of them inside the definition of a single texture object, but they're obviously identifiable by the first parameter here. And all these other parameters are exactly like they were when we did a simple texture map. Okay, so let's look at this example. So here's what we're going to do is I'm going to do the rotating cube inside of another cube. So what I did for this example, and I'll show you that too, is I said, well, let's suppose I put a totally reflecting cube, so it has no color of its own. It's like formed of 6 mirrors, and I put it inside of another cube and those will form the walls of the room that it's inside of, and each of those are a solid color, so red, green, blue, cyan, magenta, yellow. Well, if they're a solid color, then the texture maps for each of those walls becomes just a single color. All I need is a single texel. So here they are. I'm defining 6 texture maps, but if you look at them, each one is just a single texel that has one of the colors: red, green, blue, cyan, magenta, yellow. It just sort of reduces the storage. If these were more complex images, everything would work exactly the same. So just simple to do this. And now I form the texture object, which looks, here they are. It's pretty much as I did it before. I say, okay, I bind the texture maps, the texture image, to say, okay, I'm creating a new texture. I bind it, then I define 6 images instead of 1, and here it's sort of telling you it's a 1-by-1 image. And then I make act using texture unit 0, and then I use a uniform variable to link that to something called text map back in the JavaScript file. So this is this is the JavaScript file connecting it to the fragment shader where it's called text map. Okay, what do the shaders look like? Well, let's take a look at that. What you're seeing in here, and without going in detail, because a lot of this is stuff you've seen before. Basically, I have to send over all the same information I would have had to send over before. I have to send over a projection matrix. I have to send over a model view matrix. I have to send over the normals to that surface, the positions of the vertices. They're all set up in arrays. Well, the position and the normals are set up as arrays inside the JavaScript file. The model view matrix and the projection matrix are going to stay the same for that whole cube, so we send them over as uniform variables. Now I can use the reflect function down here to compute the reflection direction from the eye position and the normal that I send in. Now remember, if you remember back to our examples a few weeks ago, that I have to, if I look at the frames I'm working in, that if I use if I compute GL position, which is multiplying the projection matrix times the model view matrix times the position that comes in, that puts me into clip coordinates. But I want the reflection vector to be in camera coordinates, of the way I'm doing it here. And so I only want to I want it to be in camera coordinates. So all I'm multiplying by is the model view matrix. So I create a variable called eye position, which is the vertex position in eye coordinates, and then the normal is also computed in eye coordinates. Compute the reflection direction by using the reflect function. That is sent over as a varying variable over to the over to the fragment shader. So they're using the rasterizer now to interpolate that across the surface. And notice that all of these things, that these guys down here, the projection matrix, and it computes the position as usual, but the eye position in camera coordinates and the normal in camera coordinates are only there to compute the reflection direction. So as far as the fragment shader is concerned, all it really needs is the reflection direction to get its texture coordinates. It doesn't need any of this other stuff. The position has been determined over here. So the fragment shader, it turns out, is really, really simple. It's just standard, almost exactly what we had before. In this case, the fragment color is totally determined by the texture color, and the texture color is given by a texture cube sampler that takes in the texture map, the texture object that I formed on the other side, and then goes off in the reflection direction to get the texture coordinates. So it's very, it's almost a trivial fragment shader to do. It's a pretty complex operation involving 6 texture maps. Okay, before I show you an example, let me show you make a couple of comments on sphere mapping. That was the original way that it was done. Blinn proposed this quite a while ago. They used a mapping that was based on using longitude and latitude and parametric representation of the sphere. That, of course, gives you some distortion, as we've talked about at the poles. Again, look at the book. We have the equations that are done. It's done automatically before you in desktop OpenGL. But if you wanted to implement it yourself in a vertex and fragment shaders, you certainly could do that. But here's a little picture of a sphere map of the same thing. This is something we do inside planetariums. So we take those images, we then form. Okay, let me finish by showing you this this image of the cube inside of the box. It's reflecting the walls of the box on it. I can stop the rotation here. Let's see. It's really hard to tell that this is correct. I and other people have puzzled over this, but I think it is. So what you're seeing is the corners here where the 3 walls meet on the thing, and that's being reflected here. See, it depends very much on where the viewer is and where this cube is relative to where the walls are, but you can start it rotating again. But that's a little clearer. You're seeing as it rotates, it's reflecting different surfaces back in. That's in a program on the website called Reflection Cube, and it'll give you some idea of how you do cube maps. Okay, so next lecture we'll start talking about bump maps.